So I thought I would show you another example of designing a pushdown automaton using the following technique. I would like to come up with one using simpler PDAs and then assembling them accordingly. Now, I want to consider this language. This is a rather interesting language. It's going to consist of strings of this form. It's going to have A to the I, B to the J, C to the K, where all of these I, J's, and K's are at least 0, but it has to be that either, at least one of the following have to be true. It has to be that I is equal to J or I is equal to K. So notice that it has to have equal numbers of A's and B's, or it has to have equal numbers of A's and C's. It can have at least one of those two in play. So what I was going to suggest to us, if you look at this and say, okay, well, it has this property and it is this or this. One natural thing to try is design a PDA such that this is true, and try to design a PDA where this is true, and then try to connect them or stitch them together such that you can go to one or the other. As long as we have some sequence of IDs or moves corresponding to those IDs that gets me to accepting via final state, we're okay. Consider L1, which is just going to be the same thing we have up here. A to the I, B to the J, C to the K, such that I, J, and K are at least 0. And it has to be that I is equal to J in this case. So notice that by considering a simpler one, it makes it a little easier for us to play around with, right? So what I'm going to do is I'm going to think about this a little bit more carefully. Now I'm just going to have it where I'm going to make the input symbols the same as the stack symbols, just because it's a little easier to play around with if you think about it like that. So here we go. Let's look at what this means. If I is equal to J, that means that there's equal numbers of A's and B's for any one string in this language, and we don't care how many C's there are, right? This should remind you of one of our previous examples. So let's do something just like that. So we're going to design a PDA. We'll call it P1. Now that you know, we're going to be counting A's and B's, right? But we want to have an equal number of A's and B's, right? So that means that I'm going to be pushing symbols for A's, and I want to pop them for the B's, and I don't care about what C's going on with C. But we have to still consume those, right? So we're going to have Q's. I'll call this one Q1. I'm going to deliberately give them different names because I'm going to be assembling these. But it doesn't really matter. They're just names, right? So I'm going to have 3 phases just like we had in our previous example. I got epsilon, Z0, Z0, right? We want to make sure we can still get over here. But it may be the case that we're going to have it where we're going to push a bunch of A's onto the stack for each A, and then we're going to pop the A's on B's. So if we see an A, we're going to push an A onto the stack. If we see an A, of course, if A is on the top of the stack, if A is on the top of the stack, I want to push another A. However, if I get a B, what do I have to do?
It's poppin' time.
I have to pop the A's, right? So A will be on the top of the stack in this case, and I would pop it. And then lastly, I want to be able to get back over here now that the stack has been cleared out. So the stack's been cleared out. But I need to consume those C's. And they can be any number of C's. They could be 0 or more. So I'm just going to have a C here. I'm not going to do anything with the stack. I'm just going to leave it as is. I'm just going to gobble up the C's as they appear. And then I'll be still in Q3 anyways. So I'm going to call this one PDA P1. It's not terribly hard from what we've seen in the past to see that this is in fact going to indeed recognize this language via final state. And now let's consider another PDA for that one over there. So this is the case. So the first one is in the case when we have I is equal to j, right? The second case is when we have I is equal to k, right? So we're going to consider L2, which is going to be the same a to the I, b to the j, c to the k, such that I, j, and k are at least 0. And it has to be that I is equal to k in this case, right? So let's do something very similar, but it's going to be we have to be a bit careful now because let's see what this means. So now this is saying that there's equal numbers of A's and C's, but we can have as many B's as we want. It can be 0 or more, right? So here's what I have in my head, because now we don't have this property where we can just stick around over here and just keep gobbling up C's, right? We have to make sure that there's an equal number of C's than there are to A's, right? So we're going to have to designate a state for doing this because B's, there could be any number of B's, right? So I want to make sure I've accounted for that. So we're going to have 4 states this time. That's at least a pretty good idea. We're going to start off at Q4. I'm going to give it name Q4. So my whole point at the end of this is I'm going to try to combine these. Q4, Q5, Q6, and Q7 is going to be the final state. So naturally, I'm just going to make sure there's some pathway to get over to that final state. But remember, it may be the case that there's some A's still on the stack, right? So the purpose of this one's for pushing A's. This one's for reading the B's. This is for popping on C. So that means we're going to gate off. We want to make sure we gate off Q7 from Q6, ensuring that we definitely have gotten rid of all of those A's that we're going to push on for corresponding C's that we're going to try to match up. So we're going to do the same thing we did over here. We're going to push some A's. A, Z0, A, Z0. And on A, with A's on the top of the stack, we're going to push another A. Here, if we see a B, we want to gobble up the B. It doesn't matter if it's Z0 on the top of the stack, we don't touch it. If it's A on the top of the stack, we don't touch it, right? We just want to make sure we can gobble up all those B's. We're very hungry like that. However, we have Q6. This is where we're going to need to do. So we're going to pop off wherever we see a C, we're going to pop an A off the top of the stack. So whenever there's a C, we're going to consume the C and we're going to pop an A. And by gating it off like this, we've ensured that the stack has to be where it just has the start symbol on it. Otherwise, you wouldn't have equal numbers of A's and C's, right? So we're going to call this one PDA P2. So one thing you should look at very carefully here is that L1 and L2, if you take the union of these two languages, you get this one. You get language L. L is equal to L1 union L2. So take P1 and P2 together. Make a new start state. So this is something that you might have seen when we were exploring epsilon NFAs. We can do something very much like this here. So make a new start state, Q0, and introduce epsilon moves to the old start states. So what I'm saying is we're going to do the following. Check this out. and allow it to have a move on epsilon. Or it can freely move to Q1 or Q4. So it can do it at the same time, right? If you want to think about it like that. So notice that because it's an epsilon move, it can take on the pair associated with these that take them associated to each one of these pathways of sorts. So it might accept here, it might accept there, or it might accept both. As long as at least one of those two is satisfied, we're okay, right? So I've introduced epsilon moves, and now this is a PDA for L.